Hello, my name is Gareth Hardwick, and I'm going to be talking about distribution calibration, a few-shot learning method. To achieve high accuracy, image classification networks are trained on huge sets of labeled data for a really long time. Unfortunately, having thousands of images of each class is simply impossible for many applications in the real world. Achieving high accuracy with few labeled samples is the goal of few-shot methods. The few-shot problem is constructed as such. N novel classes, unseen by the classifier we're building on top of, are added, each with k samples. This n times k set of labeled images is called the support set. This is the set on which we will train our new classifier. The classifier classifies images from the query set, which are unlabeled, into the n novel support classes. The query set typically contains an equal number of new images from each of the n classes in the support set. The most common NK tasks are generally the 5-way one-shot and 5-way 5-shot tasks. For the purposes of my project, I stuck to the 5-way one-shot task. To begin, we require a backbone network trained to classify images into the base classes, which have sufficient data. We leverage the existing network's training by using its encoding layers, which have already been trained to extract features from hopefully a wide variety of images. Thus, the only layer we need to train is a final linear classification layer that takes us from the feature dimension to the class dimension. For this project, I used the OmniClot dataset. This dataset consists of 1,623 characters from 50 different alphabets from around the world, each with 20 hand-drawn examples. Since only k samples from each class are available to the classifier, overtraining is almost guaranteed. This is obviously problematic if the samples we have are not a good representation of the ground truth distribution of their respective classes, as you can see below from this illustration of Yang et al. To fix this issue, we can generate more data. Of course, without more than k samples from each class, we cannot hope to approximate the ground truth distribution, which would render our generated data useless. But this is where we make a simple assumption. If x, a sample from novel class I, is close to the mean of base class j, mu j, then we will assume that the distribution of vectors from novel class I is similar to that of base class j. This is the distribution calibration. Specifically, we will find the nearest kappa neighbors of each novel sample from each class, measured by Euclidean distance, and then, using statistics calculated from the base classes, we define these new statistics, mu prime and sigma prime. Note that mu prime is essentially just the mean of the average of the nearest neighbors to x, and sigma prime is just the mean of the covariances of the nearest neighbors to x, plus alpha, which is a parameter. Hence, for each of the novel classes, we will have k mu prime sigma prime pairs of statistics. From each pair, we can generate little n samples with multivariate normal distributions defined by the statistics pair we just calculated. Let's fine-tune the parameters. For any given data set, the parameters kappa and alpha can be adjusted. Kappa, recall, is the number of nearest neighbors we used to calculate the calibrated statistics, and alpha is applied to the covariance matrix and essentially will give us more or less spread in the generated features. First, I fine-tuned kappa. Note that the lower line is created from the classifier using only the support data. The upper line is the classifier when trained on the support data and the sampled data. Kappa equals 6 achieved the greatest accuracy. Next, I fine-tuned alpha. In this case, alpha equal to 0.21, the same as in the paper, achieved the best accuracy. With these parameters, I ran lots and lots of trials. The classifier trained on both the sample data and the original support data averaged 68.8% accuracy, while the classifier trained on only the support data averaged 64.2% accuracy. Hence, this distribution calibration yielded an increase in 4.6% accuracy. Thank you very much.